final section in thermodynamics and in this chapter is mathematical aspects of the second law. And it is also the last section of the last chapter for the first semester of this course in introductory physics. This is probably one of the deepest and most complex of the things that we have discussed this semester, and in my opinion and in the opinion of a number of other people, the whole concept of order and disorder, entropy, the era of time, and things of this nature are still not totally understood. From the quantum theory point of view, we can say that all of our processes are reversible. Yet we know in actual fact that when we get down to the real life, the red wine that spills on our white carpet is irreversible. Even though it has enough energy to all jump back into that glass, it's not going to do it because disorder has taken place. When you have a party, you can rest assured that things are not going to be automatically cleaner and more organized after the party than they were before. You're going to begin with things very organized and structured, and by the time everyone goes, you'll have chaos and dirt and disorder everywhere. Well, it is this second law that addresses this increase in disorder. And it's because basically disorder is much more probable than order is. So a system that explores all the possible states that it can exist in, it turns out that order is very rare, extremely rare, and disorder is very common. For example, the molecules could all be in one corner of the room. If we imagine a room here, we'd say, let's take all the air and put it right up here. Well, if we release the door on the side of this, the air rushes out and fills the whole room. But it would certainly, all the air in the room would never just suddenly go up here, although that's technically possible for it to happen. That's because there's so many ways for the molecules to all be rearranged that on the average, with Avogadro's number, or many times many moles of the gas, it's never going to happen that all of them are going to choose to be in this one particular place. That's too rare an event. So the common event is for them to be evenly distributed. Well, let's look at what happens with entropy in our formal definition. The symbol for entropy is S, which measures the disorder, and the change in entropy when heat enters or leaves a system that's reversible at a constant T is equal to the change in the heat divided by the temperature. Well, this is an incredibly important and famous equation, and this is for a reversible system. Now, we can take this and we can look at how this entropy changes for two things. We could take something like an ice cube and take a large rock or stone and let this ice cube melt. And let's pretend there's no air here. So let's allow all the heat from the rock to come up here and melt this ice cube. So you'll notice that we're looking really at a hot object and a cold object, and the heat is going to flow from the hot to the cold. Now the amount of heat that flows, delta Q, is going to be fixed. It's going to flow out of this one and into this one. So you're going to have a change in entropy that would be delta Q divided by a change in entropy, delta S, is going to be delta Q over the temperature of the hot place, of the cold place. This would be our gain minus the loss, which is delta Q over T of the hot place. Now, why is this larger than this? That's because you always lose this heat from the hot place. You always gain it in the cold place. And therefore, if you think about this, this is a smaller number. Therefore, when I divide it into that same number, this is larger than this, always. So the entropy always increases. So I give to you as a homework problem to think about how you would calculate a large rock of some large mass with an ice cube that melts on top of a given mass, how you would compute. And you know how the change in heat from the point of view of melting. Take your ice cube at a temperature of 0 Celsius. So it's ready to melt, and you can use the actual specific heat for for ice there, the latent heat of fusion, and that's what you'll need in order to compute this amount of heat at a given temperature, and see if you can compute how much entropy change there is when this ice cube melts. Again, entropy is a measure of system disorder, and try that problem of the melting ice cube. Again, I give you as an exercise, in addition to that, to think about disorder and how you measure it. And there are two places where disorder is measured. One is in thermodynamics. The other is in the area known as information theory. And there also we're measuring entropy, and we can also regard that as the negative of that entropy as a measure of how much information that we have. Information is considered a measure of how much order we have. So, for example, if you take 8 bits that we need to make up a letter, the ones and zeros, here are 8 bits. And this might correspond to something like a capital letter B. And you can see how much information is here, and that the unit of information in information theory is taken as the fundamental of a bit of 1 or 0. So the information here is 8 bits of information, because there's a plus or minus or 1, 0 aspect to each one of these, and there are 8 of them, so there are 8 bits of information altogether. So there are about 8 bits for each character we have, or number or symbol that we have in the English language. This is called a byte. So 1 byte of information is equal to 8 bits. And a byte is a character. It could be a 6, or it could be a tab, but it's some symbol that's used or can be typed on a keyboard. Now the 8 bits represent that, and you can see that 2 to the 8th power is going to give you 256 different characters, which is more than we need to make the common alphabet, and all of the symbols and the invisible things like a space and a tab and ringing a bell and a line advance and things like that. So this is perfectly adequate. We can actually do it with about 128 and then use the other bit as what's called a check bit, to make sure that no bits were dropped and the information is becomes slightly redundant. But this is the standard that we use. Of course, today's lettering using foreign languages, we've gone to a Unicode system where we use 2 to the 16th. So we're actually using 16 bits, which gives us a very large number of characters and allows us to represent every language on earth with all of the symbols in their alphabets and so forth. So if we look at this organization, then you can see that this is very unlikely to have this letter B. You could have any random thing here, and of course you don't have much information. If you don't know whether this is a 1 or a 0, if it has a probability of a half to be each one, then that would be the maximum disorder that you could have, is where each bit, you can't tell whether it's a 1 or a 0. That would be the maximum entropy, like a weathered stone, and you can't really read whether the 1s and 0s are one value or another value. And so there's a 50-50 chance for each one. That would be the maximum ignorance that you could have, and therefore the maximum entropy. This would be the maximum order, or the least entropy. Combining these two concepts of information theory and thermodynamics is certainly not trivial. And looking at information and entropy is really a study of all processes where you're looking at order and disorder. So we're really measuring this by entropy, and we're measuring this by information. Now, to tell you how complex this topic is, let me ask you the following question. If I take a poem by a 3rd grader and I compare that to a poem of the same length written by someone like William Hugh Auden or T.S. Eliot, the T.S. Eliot poem will contain much more order and information, yet they have the same number of characters. But the information here is going to be much greater. How do we measure that? Even worse, how do we compare a poem by T.S. Eliot on the one hand with a painting by Salvador Dali? Which has the most order? Is that just the bits of information? No, it's much more subtle. And how do we compare that to force is equal to dP dt, Newton's second law, and all of the different phenomena that this describes? We have no idea how to measure this. So we're really very ignorant about how to understand order in the universe and disorder. And certainly, the universe tends towards disorder. And there was a time early in the 20th century when this was first discovered and we understood heat engines that people were really worried about what is called the heat death of the universe. That's where all of the useful energy was uniformly distributed. Everything went to maximum entropy. The stars burned out, and we just had one cold universe with no energy sources. And that's the prediction of what a thermodynamic eventual end state would be. And it's very frightening to think that everything just freezes up and there's no source of energy, but there's perfect disorder. Anyway, that should be enough to stimulate your imagination and get you to try to think about these types of questions. How do we measure order and disorder? How do we measure information? And how do we combine this concept in information theory with these concepts in thermodynamics and randomness and statistical mechanics? Those are very complex questions. And I hope you enjoyed this semester.